In the previous lecture, we had studied two psychrometric processes. One was a diabatic mixing of two moist air streams, and the second one was sensible heating or sensible cooling. Continuing with the psychrometric processes, the next process is that of humidification, in which we add moisture to a stream of air which is entering a duct, and the process is carried out by spraying water either in the form of a liquid or steam into the air stream, and it is assumed that all the water that is sprayed into the air stream is retained by the air as it leaves the duct, and the duct or the chamber in which the humidification process is carried out is perfectly insulated, so there is no energy exchange from the surroundings. We can perform an energy balance on the air stream at the inlet and outlet, and we can also perform a mass balance on the water in the air stream at the inlet and outlet. And the equations for the energy balance and the conservation of mass are given to us, and it is quite straightforward. That is, if we want to look at it, the energy content of the air when it is at state 1 at entrance to the duct is m dot A times H1, and to this energy content we add the energy which is brought in by the water that is sprayed. That will be m dot W HW. So m dot A H1 plus m dot W HW, and that must be equal to the energy content at the end of the process at state 2, which will be equal to m dot A H2. And if we just rearrange the terms by taking the terms which have m dot A on one side, we will get the expression that m dot A H2 minus H1 is equal to m dot W HW. Similarly, if we look at the conservation of water in the air stream, remember the mass flow rate of water vapor is equal to the mass flow rate of dry air into the humidity ratio. So at state 1 we will have m dot A into W1, to which we have added the water at the rate m dot W, and at the end of the process we will get the mass flow rate of water, which will be equal to m dot A times W2. As before, we collect the terms which have m dot A on one side, and you will get m dot W is equal to m dot A into W2 minus W1. And these two equations can be further combined together to get the result in the form of the ratio delta H by delta W. All we have to do is to divide this first equation from the energy balance by m dot A throughout, and on the left hand side you will get delta H, on the right hand side you will have m dot W by m dot A into HW, and m dot W by m dot A from the conservation of mass for water will be equal to delta W. So you will get delta H is equal to m dot you will get delta H is equal to delta W into HW, and you can take delta W again on the left hand side, which will give you the expression for the ratio delta H by delta W, which is equal to HW. This expression, you will see, has a certain utility for us when we sketch the psychrometric process on the psychrometric chart. If you look at the representation of this process on the psychrometric chart, you can see that the humidity ratio at the end of the process will be higher than the humidity ratio at the initial state. And I can just draw one line to show a increase in the humidity ratio. From state 1 we can reach this humidity ratio by a number of different paths that are shown over here, and there are three distinctions between the paths that are shown over here. You can see in the, if we look at the process line 1 to 2 prime, it shows an increase in the humidity ratio, but at the same time there is an increase in the dry bulb temperature. So although we have just humidified the air, but at the same time a secondary effect is that the dry bulb temperature has increased, and this will be possible if the enthalpy of the water that you are spraying is greater than the enthalpy of saturated vapor at state 1, that is HW is greater than Hg1. Under that condition we will obtain the line, process line 1 to 2 prime. On the other hand, if HW is less than Hg1, then we will have a process line which is shown by the process line 1 to 2 double prime, and this time you can see again we have an increase in the humidity ratio, but this time the dry bulb temperature has decreased. That is, we have evaporative cooling. So that is a second possibility for the humidification process to proceed. And the third one you can see is 1 to 2, in which if we reach the same humidity ratio, what is different this time is that the dry bulb temperature remains unchanged, and that is pure humidification without any heating or cooling of the air, and that will be only possible if HW is equal to Hg1. That is the third possibility. For the humidification process. What I can do, just to show you that this actually is the case, I can take initial state on the psychrometric chart, and then we can see what will happen if we spray water in liquid state, which is typical of the condition that HW is less than Hg1, or when we spray steam for which HW will be greater than Hg1, and we should obtain the two different process lines as sketched over here. The third process line will only be possible if you are spraying water at a very low pressure corresponding to the saturation pressure at 1, and then it should be a vertical line. So I will go through an example in which I have already marked a state point on the psychrometric chart, and you can see the dry bulb temperature is 34 degrees and the relative humidity is 30%, and at a dry bulb temperature of 34 degrees the enthalpy of saturated vapor can be read from the table for water, and you can see at 34 degrees C the saturated vapor enthalpy is 2563.6 kilojoules per kilogram. We will return to this table later. Before we do that, we go back and then we try to see how we can draw the process line when we are spraying water, let's say at 26 degrees C, and then we will repeat the process when we are spraying steam at 110 degrees C. And for that we will make use of the equation delta H by delta W is equal to HW, and you will also see that when I do that I will introduce you to the use of the protector, which is shown on the top left hand corner of the psychrometric chart, which has two scales, one on the inner side which is sensible heat by total heat, and on the outside you have that ratio delta H by delta W. This protector is quite a useful tool for processes in which you have either addition or extraction of moisture, that is there will be a sensible heat content as well as a latent heat content. And as I said, I will start with water at 26 degrees C, and for that I will again move on to the table, and you can see at water at 26 degrees C, because it's liquid, the enthalpy is 108.95 kilojoule per kilogram. So that means delta H is 108.95 kilojoule per kilogram. Delta H by delta W is 108.95 kilojoule per kilogram. Delta H by delta W is equal to HW. But on the scale you can see that the numbers are quite small, whereas we have a HW value of 108.95 kilojoule per kilogram, and that is because on the psychrometric chart the humidity ratio W has units of grams per kilogram dry air, whereas in the SI system they are kilogram per kilogram dry air. So we need to first convert this value of HW from kilojoule per kilogram to kilojoules per gram, and that means we have to divide it by 1000, and when we divide it by 1000 we get a value of 0.11 kilojoule per gram, and that value we can now read on the outer scale. And to draw the process line from state 1, I'll just label it. We have state 1, and I will draw the I have to draw the process line. Now to draw the process line I need to know the slope of the process line from point or one or from state 1, and that is obtained from the protector. What I will do, I will go to the protector. This is the origin of the protector, the cross that you can see at the middle, and from there I will go to the reading of 0.11 on the outer scale. This is 0, and we have increments of I think 0.2, 0.24681. So this is 0.2. 0.11 is almost in the center. In fact, this point, so 0.2, so 0.1 will be somewhere over here. And what I now have is the correct slope of the process line on the protector, and all I have to do now is to draw a process line in the psychrometric chart from the given state, that is state 0.1, which is parallel to this line. So if I draw a line which is parallel to this line, that will give me the correct slope of the process line when we are humidifying the air by injecting water at 26 degrees C. So I can just simply take it over here. And that will be the process line, and it shows humidification as well as a decrease in the dry bulb temperature. Then I told you that the second possibility is that of injecting steam at 110 degrees C, for which I will again look at the value of HW. Now this time, because it is steam, HW is equal to Hg at 110 degrees C, so that means it is equal to 2691.3 kilojoules per kilogram. As before, that kilojoules per kilogram value has to be converted to kilojoules per gram, which comes out to be 2.69. And I again go to the protector and then draw a line which has a slope of 2.69. So this is 2.5, this is 2.6, this is 2.7, and 2.69 is just before 2.7. And again I will draw a line parallel to this line from the state point 1, and that will give us the correct slope of the process of humidification when we have injected steam. And you can see again that the humidity ratio has increased, but at the same time the dry bulb temperature has also increased. The third one possibility was that when HW was equal to Hg, and if I want to find out Hg, I have to look at the value of Hg at 34 degrees C. So if I go back to the table and look up 34 degrees C, at 34 degrees C, Hg is 2.563.6 kilojoules per kilogram, which will be 2.56 kilojoules per gram. And I can then draw the third process line with the help of the protector. We have got 2.5 over here, and we need a value of 2.56. So this is 2.5, this is 2.6, so we are just about over here. And then if I take this over here, you can see I've got almost the same line without any change in the dry bulb temperature. So that is a verification of the conditions that we had identified when the humidification process is being carried out. Then we will further look at the case of humidification using liquid water, that is when HW is less than Hg1. And for that particular case, there are further three possibilities. And they are again described to you, that if the water is injected at a temperature which is equal to the wet bulb temperature of air at state 1, it will follow the constant wet bulb temperature line, that is 1 to 2 asterisk or 2 star. If the temperature of water is less than the wet bulb temperature of air at state 1, we will follow the process line 1 to 2a. And the third one is that if the temperature of water is greater than the temperature of wet bulb temperature of air at state 1, we will follow the process line 1 to 2C. We will now move on to an example in which we will use the results that we had obtained for the humidification process to solve a simple numerical. We are given the condition of moist air in terms of the dry bulb and wet bulb temperatures, and the air is being humidified by using saturated vapor at 110 degrees C, and you are asked to find out the humidity ratio and the dry bulb temperature at the end of the humidification process. What we will do is first locate the state point on the psychrometric chart, and as I told you earlier, you have already identified the process and sketched it at the beginning, and then you move on to the psychrometric chart. So when you locate the state point on the psychrometric chart, you will be able to read the humidity ratio and the specific enthalpy, which I have already shown in the solution as 1.9 grams per kilogram dry air and 27 kilojoules, and these values we can confirm by going to the psychrometric chart. I have already located the state point at a dry bulb temperature of 22 degrees and at a wet bulb temperature of 9 degrees. Okay. You can see this is the constant wet bulb temperature line. The dotted line over here is a constant wet bulb temperature line, and this corresponds to 9 degrees. This one is for 10 degrees. And the humidity ratio, you can see we are just under 2 grams per kilogram dry air, so that was 1.9 gram per kilogram dry air, and the constant is specific enthalpy lines we can draw any one from over here. And if I just take it to the desired state point, you can see this is 20, so this is 22, 24, 26, and this is 27 kilojoules per kilogram dry air. So those values we have now confirmed, and what we need to do is to then see how we can identify the end point of the process. The end point of the process can be worked out by using either the equations that we have or the equations in conjunction with the protector. First, I will solve the problem by using just the equations. The end point of the process will only be located if we know two of the properties at that end point. One of the properties that we can easily find out is the humidity ratio by using the equation for the mass balance of water vapor, that is m dot w is equal to ma into w2 minus w1. M dot w is given to us in the problem statement, and so is the mass flow rate of dry air. Make sure you convert the values given in the problem into SI units, that is in kilogram per second of moisture and kilogram dry air per second of dry air. Then humidity ratio we have already found out from the psychrometric chart, and the only unknown will be W2. So you can find out W2, and you can see that the value of W2 comes out to be 11.5 grams per kilogram dry air. And again, I will go back to the psychrometric chart and mark out the value of W2 on the psychrometric chart, 11.5. So if you look at it over here, this is 10, 10.5, 11, 11.5 will be over here. So we know that once we start from state 1, we should end up on this horizontal line where the humidity ratio is 11.5 grams per kilogram dry air. Where on this horizontal line we will end up, we don't know yet. We need a second value of a property at the end of the process, and that will be worked out by using the equation we had for energy balance. That was m dot a into h2 minus h1 is equal to m dot w hw. Hw we will get from the table. At 110 degrees C, the humidity, enthalpy of saturated vapor was 2691.3 kilojoule per kilogram. Mass flow rates of air and water are given in the problem. H1 we have found out from the psychrometric chart, so all we need is H2, and the value of H2, if we go back to the solution in the lecture notes, it comes out to be 52.8 kilojoules per kilogram dry air. Now you go back to the psychrometric chart and then draw a line which a constant enthalpy line which corresponds to a value of 52.8 kilojoule per kilogram dry air. So 52.8, we are almost close to 53. So I have to just move this to, this is 52 and 53, 52.8 is just around here. Okay. And the intersection of this line with the humidity ratio line of 11.5 grams per kilogram dry air gives you the state point at the end of the process, and that is point number 2. And what we can now show is the process from 1 to 2. We were asked to find out the humidity ratio and the temperature. Humidity ratio we have already found out that to be 11.5 grams per kilogram dry air, and to find out the dry bulb temperature at state 2, we can just read off that value from a line drawn vertically downwards. If this is 20, this will be 21, 22, 23 point, roughly 23.5 degrees C, and that is the dry bulb temperature which we have over here. So that's one way of solving the problem, just by using the equations. I told you that we can also use the protector to solve this problem, and to do that I will once again go back to the psychrometric chart and go back to that step where we had found out W2. We know that we have to start from 1 and we have to end up at W2, and the slope of the process line can also be obtained by using the value HW, which is equal to Hg at 110 degrees C, which was 2.69. So if I go to the protector and draw a process line with a slope of 2.69 kilojoule per gram, so this is 2.5, 2.6, 2.69, this is 2.7. The 2.69 I expect is somewhere over here. This is just a approximately drawn line, and then I will draw a line parallel to this line and you can see the intersection of these two lines must again give us the same endpoint of the process. Okay. And again, if you want to read the dry bulb temperature over here, all you have to do is to drop a vertical line and the temperature is 21, 22, 23, again 23.5 degrees C. So you have the option of using the protector in your solution or just working out with the equations if possible, but keep both the options open to you and make sure that you are familiar with the use of the protector. The next process that we are going to study is heating and humidification. We have studied heating separately and humidification separately, and this is a combination of the two processes, that is of sensible heating combined with humidification, and that is schematically shown in the figure with the corresponding process shown on the psychrometric diagram. You can see from state 1 to state 2 the air undergoes sensible heating. At state 2 we inject steam into the air for humidification, and process 2 to 3 shows the humidification process. The resultant process of heating and humidification is shown by the process line from state 1 to state 3. The mathematical equations of energy and mass balances are straightforward. If you look at the sensible heating process, the energy content at state 1 will be m dot A times H1, to which we add the rate at which heat is absorbed by the air from the heating coil, that is Q dot, and at the end point of the sensible heating process, that it is at state 2, the energy content will be m dot A times H2. So m dot A H1 plus Q dot is equal to m dot A H2. We can rearrange that equation to obtain equation 1 that we have in our lecture slide. Then we humidify the air from state 2 to state 3, and if we look at the mass balance for the water vapor, the amount of water vapor m dot V is equal to m dot A times the humidity ratio. So at state 2 we will have m dot A times W2, to which we will add steam at the rate m dot W, and the resultant amount of water vapor at state 3 will be m dot A times W3. So m dot A times W2 plus m dot W is equal to m dot A times W3, and again rearranging that equation we get equation 2 as shown in the slide. The energy balance for process 2 to 3, the energy content at 2 is m dot A H2, to which we add the energy of the injected steam, that is m dot W HW, and we get the resultant energy content at state 3, which is m dot A into H3, that is m dot A H2 plus m dot W HW is equal to m dot A H3. Again rearranging this we get equation 3 as shown on your slide, and what we can do, we can combine these equations 1 2 3. So what you will do, you will add equations 1 and 3. When you add them together, on the left hand side, m dot a h2 minus h1, to which you will add m dot a h3 minus h2. So this term plus h2 minus h2 will cancel out. You will get m dot a h3 minus h1, and on the right hand side you will get q dot plus m dot w hw. Divide throughout by m dot w, so you will get m dot a by m dot w into h3 minus h1, and on the right hand side you will get q dot by m dot w plus hw, and m dot a by m dot w can be replaced by 1 upon w3 minus w1 using equation 2, and the resultant equation that you will get again is shown in your lecture slide, and this is the equation for the combined heating and humidification process, that is from state 1 to state 3. Based on these equations, we can again go through a example. In which we are given a certain state at the inlet to a duct of moist air at a certain mass flow rate, and it is first sensibly heated by a heater whose capacity is given, and then it is humidified by injecting steam at a certain temperature and at a certain rate which is given to us in the problem. We need to find out the relative humidity and dry bulb temperature at the end of the heating and humidification process. And the first thing that we do after we have identified that it is a heating and humidification process is to sketch it on the psychrometric diagram as we had shown earlier. So this is the sketch that you will draw at first. Once you have sketched it, labeled it properly, then you can move on to the psychrometric chart, the actual psychrometric chart for the solution. The first thing that you can do is to locate state 1 at which the dry bulb temperature and relative humidity is given. Once you have located state 1, you will be able to read off the specific enthalpy and humidity ratio from the psychrometric chart at state 1, and I will show that to you. I've already marked state 1 over here. You can see the dry bulb temperature is 20 degrees C and the humidity ratio was given to us. The relative humidity was given to us 50%, so 20 degrees C and relative humidity of 50%. So that's state 1. At state 1 we can read the humidity ratio, that is W1, which comes out to be around 7.3 grams per kilogram dry air, which you can convert into kilogram per kilogram dry air by dividing it by 1000. At the same point you can see that the specific enthalpy is 39 kilojoule per kilogram dry air. So that is the first thing that you will do when you move to the actual psychrometric chart. Then we can use the equations that we have to find out the humidity ratio at state 3, because we know are given the mass flow rates of dry air which remains constant throughout, and the mass flow rate at which steam is injected, these are given to us, and the mass balance for water vapor, that is the equation m dot w is equal to m dot a into w3 minus w2, and remember w2 is the same as w1 because from 1 to 2 we have a sensible heating process during which the humidity ratio remains constant. So in this mass balance equation, m dot w and m dot a are known. W2 is the same as W1, which we have read from the psychrometric chart, and that gives us W3, which is 0.0173 kilogram per kilogram dry air, which comes when we mark it on the psychrometric chart, we will convert it into grams per kilogram dry air, which has a value of 17.3. So again, let's go back to the psychrometric chart, and you can see I have already marked out a humidity ratio of 17.3 over here. So we know that state number 3 will lie on this constant humidity ratio line. Now where does state 3 lie? We do not know, because we need a second property at state 3 to locate that point on the psychrometric chart, and we can use the resulting equation that we had obtained, that is delta H by delta W, in which if you look at the equation, H1 is worked out, so is W1, W3 has also been worked out, Q dot is given to us, and M dot W is also given to us. HW is the specific enthalpy of a steam at 100 degrees C. You will read that value from the property tables for water, that is table A1, and that is 2676 kilojoules per kilogram. So insert these values over here, and the only unknown was H3, and H3 comes out to be around 68 kilojoules per kilogram dry air. And now we can go back to the psychrometric chart, and you can see I've drawn a constant specific enthalpy line where the value of the specific enthalpy is 68.3, approximately 68.3 kilojoule per kilogram dry air, and where this constant enthalpy line intersects the constant humidity line corresponding to state 3, that is the point indicating the state of the air at the outlet. Once we have located state 3, then we can read the relative humidity and the dry bulb temperature. You can see the relative humidity is slightly above the 90% relative humidity line, that is around 92%, and the dry bulb temperature is slightly less than 24 degrees, around 23.8 degrees, and these are the values that I have finally given as the answer. That is T3 is 23.8 degrees C and phi 3 is 92%. That is all for this lecture, and we will continue with the remaining processes, of which there are only two now. One is cooling and dehumidification, and the other is heating and dehumidification. These I will start with in the next lecture, and once we have gone through these, we will have covered the desired range of processes that are of significance to us when we study air conditioning.